Okay, so let's look at the second inclined plane problem. So this time I'm going to ask you a question to think about this before we actually solve it and see what you think and see, let me know if your intuition is right at the end after we do the calculation. My question to you is, if I put a box like this on a slope and it's not moving, so I require it to not move. Okay, so obviously there has to be friction because gravity is going to pull it straight down. Normal force is going to reject it sort of normal, right, perpendicular to its surface. So one's going that way, one's going that way. It has to move down. So for it to not move, there needs to be friction, right? So there needs to be friction sort of preventing it from moving. Now my question is, if I wanted to have a larger friction, right? Does the mass matter? If you want something more applicable, you sometimes might say, who cares about a box on a slope? Let's say you're parking on a car in San Francisco, right? So that would be very applicable to you. So if you are parking on a very steep slope in San Francisco, do you want more people sitting on your cars to ensure it doesn't slip? And you want this to stay at rest, right? Or do you want less people in your car? You want it to be more massive or less massive if you want to make sure it doesn't slip, or the same, or will it not change it? Even if you cram 100 people in your car, it's the same as if you cram one person in the car. The friction is going to be the same. If you cram 100 person in it, will it be more easy to slide down or not? All right. So think about this first, and let's attack it. Right. Remember, it's the same. Who says physics not applicable? So we have a very real life scenario that I just made up. Well, in that case, yeah, the contact surface would be your tire, and you will need some sort of coefficient of friction. Let's say the static coefficient of friction. You can look that up just go on Google. You can look up the static coefficient. The coefficient of static friction, what is it between rubber tires and ground, right? And you can figure that out, and we can analyze this. All right, so how are we going to analyze it, right? So it starts with the 3 steps again. Draw the free body diagram, write down Newton's second law, resolve anything if you need, and identify what you are trying to solve, and equate the equations together, try to rearrange it, and so forth. All right, so the first step, draw the free body diagrams. There's only one object of interest over here. It's easier to actually approximate that as a single point on the slope instead of an extended object. But once you've done enough of these, that's fine. So you have weight. Again, usually we start with normal force. But yeah, these are the only 2 forces. But if for it to stay static, right? And that means, because with just these 2 forces, you can kind of tell the net force is going to pull it somewhere between these 2 vectors. So to counteract these 2 resultant force, there needs to be friction. And if I want everything to be static, there's static friction. If you think about it, right, just think about how would the mass affect this. What do you want, right? You want A to be 0. Right? You want this to not accelerate. Well, x or y depends on what you mean by x, y, first of all. And as we learned, it's probably generally a good idea to select x along the slope as your x. But yeah, it's not going to accelerate in either x or y because you want it to be static. Okay, so just thinking about it, what do you think? Well, if it's more massive, one school of thought, you might think that if it's more massive, well, then the weight will be heavier. So it would drag it further down. So I probably don't, if I wanted to stay where it is, I probably don't want M to be that massive. On the other hand, what is friction? I kind of want to maximize the friction if I want the car to stay there, static, right? So, but friction, as you understand, is mu n, right? Static friction is the static coefficient. That's the maximum it can take. What's n? Well, n is related to m as well, right? The larger the m, right? The larger the mass, usually the larger the normal reaction force. So the larger the reaction force, larger the friction. So maybe I should cram more people in it. And if I cram 100 people in my car, then it will sort of ground itself onto the ground more, right? Which school of thought, or do they exactly cancel out so that cramming 100 people in and cramming one person does not matter? Which school of thought do you think it is? All right, so maybe the answer really will surprise you, and I bet it might surprise a good amount of you because so it will be a lesson that sometimes your intuition is not that correct, and you want to do your math, and you don't. One benefit of becoming a physicist, or well, you don't even have to become a expert physicist, just a basic physicist. You'll be able to answer that question: how many people should you cram in the car, if any, or if any effect at all, right? What do we do? Well, we've got our free body diagram. We want to do our Newton's second law, but we need to resolve any forces first, right? So I could use a different color just to make it more clear on the diagram. I kind of want to show you in real life, right, when you do an exam, how you do it. So you probably won't going to be switching between red and blue and green. I'll show you probably how it would look in your exam, right? So I'll draw some dotted lines like this just to know how I resolve W. And I know that's the one I'm resolving because these two already lie on my axis. This is the only one that's diagonal to both of my XY axis as I defined it. Notice I put that down and I've always made that clear. So draw a dotted line perpendicular to your XY axis. If you want, you can make that extra clear over here. That's negative, right? That's positive Y. So maybe let's not put it there. It's almost suggests that that's positive Y, which we could do, but we're not, right? That way, right? So, okay, so we're gonna break this into its X component. So it's gonna go there, and this one's going to go down here. It doesn't have to be exact, but I'm just making it as obvious as possible, right? Like this. Okay, so now we can analyze the forces in the X and Y direction. So we can write down MA equals F net. We'll write it twice because we have both X and Y. Remember, these are vectors. So it comes from the vector equation, but let's skip the vector step and directly look at this because we've done this once already, and we can just start off like this. The M, though, does not have an X and Y. M is a scalar. It multiplies, it scales, right? It's the scalar in front of the vector, just gets multiplied straight into both the top and the bottom row of that column vector. All right, so what we want is really, we want this to be 0, right? So we want this to be 0, we want this to be 0. That's what we want. Remember, what are we trying to solve? We were trying to solve what happens to M. Does that matter at all, right? So one that is 0. Another way of thinking about it is you can actually just use Newton's first law, right? Forget about second law. You can just use common sense and think, if this doesn't move, if you want this to be static, this better cancels this, and this better cancels this. So in other words, N better equals WY, Fs better equals to Wx. But if you even do it properly with Newton's second law, you can have the same conclusion. F net in the X direction, which one's positive? That one's positive, right? This minus Fs equals to 0. And on the Y direction, which one's positive? The N is positive according to my choice of Y. So minus Wy. Right? So you can rearrange this to Fs equals to Wx. You can rearrange this to N equals to Wy, but that's simply the statement of this has to cancel this. This has to be the same magnitude of this. You see the direction is already taken care of. And this magnitude, the magnitude of N better equals to the magnitude. Notice no more vectors over here. Everything's talking about magnitudes of each of these ones. You are allowed to directly just write this down as well. Then you might want to put a bracket and say this is using Newton's first law, that there should be no net force on an object. It should stay at rest if it starts off at rest. If you like, you can start off all the way from Newton's second law, which is slightly more general, but a lot of times once you've solved this once, you'll see me, if I do any future problem with static, I often just if I know it's static, it stays static, so I'll just quote Newton's first law and say that all the forces, right, the X forces, these two must balance each other, these two must balance each other. So the magnitude of these must be equal. Okay, so now you've got this. The next step is plug in any formulas, right? Identify any things and identify your aim and solve. And identify any formulas you can plug in, right? So mu S, we have a formula we can plug in. That's the maximum static friction it can take. And how about Wx? It didn't really resolve it, right? So that's theta. That's going to be theta over there. So Wx is, what is it this time? Sine or cosine? It's going to be opposite, right? This guy is going to be the sine. Sorry, the Wy is going to be the one with cosine. That's sandwiching the angle. This one's going to be sine, right? So we can just write that down. W sine theta. And this one is W cosine theta. And W is the weight, which is mg cosine theta. Sine theta. All right, what can we do? Well, I see n over here, I see n over here. What are we usually given? We're usually given the angle. We're usually given the angle, right? So that's assume known. G is known. Mass is usually given as well. That's known. So we can actually find the normal force. And once that is known, it seems almost suggestive to plug it in here and see what does that tell us about mu, which is the thing that tells us about friction. So let's put that in there, right? In fact, right, so let's actually just say this is almost suggestive, right? That it's begging you to just plug this in here and see what happens. So let's do that. So we have mg cosine theta equals mg sine theta. Once you plug in n. What does this tells us? Well, mu s, right, the m's cancel, the g's cancel, is sine theta over cosine theta. In fact, sine over cosine, we have a special name for this function, is tangent. Right? Draw a triangle, you realize this is opposite over adjacent. Sorry, this is opposite over hypotenuse. This is adjacent over hypotenuse. Divide that, you basically have opposite over adjacent, which is tangent, right? In fact, this is actually a more general definition of what tangent is. Okay, so what do we find? We find that mu s is equals to tangent theta. Well, this is the maximum amount of friction it can take. That means if you increase theta, how does tangent look from 0 to 90 degrees? Because we're not going to concern if this increases from 0, right? 0 is just flat. If this goes to 90 degrees, that's just basically vertical, it's free fall. If it's anything past 90 degrees, it's not going to follow the slope anymore. This is completely the free body diagram we started with. It's not, you cannot push it beyond the domain of validity, right? You're pushing it beyond the validity of your free body diagram. Your free body diagrams assuming there is a normal force, but beyond 90 degrees, even at 90 degrees, that's the threshold. That's just when you have no more normal force. After 90 degrees, there's absolutely no more normal force. So your whole free body diagram analysis is invalid, right? So you need to completely redo everything. So we're gonna only analyze things from 0 degrees to 90 degrees. A tangent curve looks like this from 0 to 90. We just focus on here. So basically it increases, right? So if you increase the theta, you basically need a larger mu s for it to stay constant, right? So stay static, right? So we're assuming everything is static, right? So what that says is, or if you have a higher mu s, you can support a higher theta for it to be static, right? Another way to think about it, right? This is the maximum friction it can take. So it will start moving if Wx is so what you really want is you want this to be smaller. Let's change the color of that. You want Wx to be smaller or equal to Fx. This is what you want. Okay. So another way to think about it is right. You want the net force to be smaller or equal to 0. The maximum you want is 0. We'll worry about the negative in a second, but here it's slightly more obvious. You know what? Yeah, let's not confuse ourselves with negative numbers just yet. Just start from here. Basically, this is the maximum value it can take, and the maximum, because this formula is for maximum static friction, right? So you want this guy to be less than this. That means you want this guy to be less than this, right? You want this guy to be less than this. So you basically, once you plug this in, you want this guy to be less than this, which means you want this guy to be less than this, and you want this guy to be less than or equals to that for it to be static. Okay. Right? So that's a slightly more rigorous analysis. And yeah, so the larger the angle, the larger you need this. If you have this beyond this, so if you get the larger angle that goes larger than mu s, then it will no longer be static. It will start. So this guy will win. This guy will overcome this guy. Okay, so yeah, good. So that makes sense, right? So if you increase this, you need a larger mu s for it to stay constant or stay static. How about mass? Let's go back to our initial question about mass. Does it matter? No, there's no mention of mass. In fact, you see it explicitly happen over here. That's the moment where mass gets canceled out. So this is the answer. I don't know what your intuition told you in the beginning, but you can answer that. And let me know in the comments below or in your feedback later on. Is that what you expect, right? So it turns out if you cram 100 people in it to make it more massive and less massive, when you include the friction, it just does not matter. And the reason it does not matter is you increase the weight by, if I cram 100 people versus 1 people, right? I increase the weight by 100 times, but the friction also, the normal force gets increased by 100 times. The friction also gets increased by 100 times. So if I increase the mass of something by 100 times, not only does the weight increase by 100 times, the friction also increase by 100 times, and they exactly cancel out. The only thing matter is the angle. Okay, so you can tell me, you can go and Google this value and tell me what is the maximum angle that you can park on San Francisco for the slope. So find out what that value is. Here's my challenge for you. Optional challenge, but interesting one nonetheless. Google that value and find out what's the maximum theta you can park. It does not matter how heavy your car is. It does not matter whether you have how many luggages in your car. That's going to be one single value. All right. Let me know in the comments below what you have found. And once you know that, you can know that, make sure next time you go on San Francisco, if there's slope that is steeper than that, make sure you don't put your car on park on that slope.